Understand what is going on with Fisher's exact test. And thankfully, well, I don't know if I can say that I have it 100% by any stretch, but I definitely have thought through it enough that I can talk sort of about what it is and some places where it applies, and then I guess it's a neat concept because it's very unrestrictive in terms of, I almost feel like the sky might be the limit in terms of places that you can find to use the Fisher's exact test. You have to be creative. So I've thought of 3 different examples that I use to illustrate what kind of probabilities the Fisher's exact test allows you to ascertain, and what they could possibly mean in context of something that we can imagine happening in the world. So the 3 things, okay, understanding Fisher's exact test via 3 real-world probability scenarios. So first, I'm going to show how you can defraud a psychic. If you've ever encountered someone who claimed that they had psychic powers, and you thought to yourself, well, how could we put that to the test? Well, there are a number that, there's a lot of different ways you could do that, but what I'm proposing is one specific test that has easily calculable fixed probabilities of the outcomes. And the beauty of that is you can then just ask, well, how improbably good was what the psychic achieved? Okay, so from that I'll go on, and I'd like to suggest that you can use a Fisher's exact test to gain evidence as to whether your goalie is throwing the game, whether he's intentionally letting goals in. And thirdly, you could use a Fisher's exact test to determine whether someone is avoiding you or not. And so I'm going to use the example of, well, I'll get into the example later, but it's kind of cute. It's that there's a special someone, let's say a girl, that you'd like to have chance encounters with, and you know that she goes to the library at a certain time, so many days a week, but you don't know which days, and there seems to be no real pattern. It seems to be up to the vicissitudes of life to sort of determine that. And you've given yourself a certain number of days to try to intercept her at the library, and at the end of the week you look at how many times you did run into her and how many times you didn't, and you can actually use Fisher's exact test to quantify those probabilities. Okay, so the first thing we need to do to understand this is to see why each situation that I've just described can be modeled with a hypergeometric distribution, and how to sort of solve the word problem using this model, and how to interpret the results that you get. Maybe the interpretation comes a little bit later, but I show how to sort of extract a hypergeometric probability from these situations. And secondly, we want to see that for each outcome that we could be talking about, so each point in the sample space of the hypergeometric in question, there's a unique 2x2 table. And we can use that 2x2 table to represent the problem, and it can become a handy tool for sort of reading off the hypergeometric distribution parameters, or also there's sort of a quick formula that lets you bypass formally doing the hypergeometric, even though that's what I suspect, though I won't prove that that's what the formula is derived from. And then I'm also just going to show the idea that we can conduct odds ratio inference, what, well, I sort of trailed off here. I don't know, like I talked a little bit, I compute some odds ratios, but I'm not very happy. Like burning question that something I need to go look up is like limits of odds ratio. Let's do lambda. In terms of cell counts, well, I know that if there's a 0, it destroys your odds ratio. I'm just wondering if like you need a certain number of cell counts to use the procedures. I'm sort of thinking that you do, but we'll leave it there for a sec. Okay, so in the psychic example, here's what's happening. I want to test a psychic's claim that they can do better than chance on knowing if the unseen side of a card is marked. So I've designed the following experiment. I'm going to take 10 cards, and I'm going to put a little mark on the back of 5 of them, and then I'm going to pile the cards up, and I'm going to shuffle them. And I'm going to hand them to the psychic, and I'm going to say, okay, you're going to go through one by one each of these 10 cards, and you're going to decide which 5 you think I've marked. And you're going to indicate that on the face of the card. So then it would simply be a matter of taking each card and looking for a yellow dot and or a red dot to determine whether it was like a success. Like this time the psychic got it. But that was the only time. So what I claim is that if the psychic is legit, the probability of them correctly identifying as many or more cards as they do should be at the very least half. And it would be nice if they did something really spectacular. So let's say I'm making up the probability, but let's say in this scenario, like, there's a 50% chance that they would get like one or two cards correct. Well, then they'd better like do better than that, because I would say that like by chance you could have gotten 2 cards, or you know, that would have been a likely scenario. So anyway, this is like the kind of evidence I'm looking to compare their performance to just like a theoretical sort of if their choice was completely random, what would be the expected number of successes? And they'd better perform better than that. Okay, so my next big pressing question here. How is this a hypergeometric? Well, this is where like you have to use a bit of imagination, and I don't know if isomorphism is the correct word, but in essence, there's like this hypergeometric scenario which involves like having an urn with a fixed number of balls in it and a fixed number of balls of interest, in this case the yellow ones. And the way the scenario goes is you stipulate a sample size, so say you're going to grab 4 balls. You can then answer the question of, well, what's the probability of 1, 2, 3, or 4 of those balls being yellow? So the thing that you have to see is that the situation with the psychic and me could like sort of map onto this, in that, you know, the yellow balls are now cards that I've marked yellow on the back of. The black balls, or the not successes in the population, are represented by the cards that I haven't marked at all. And essentially, what the psychic is going to do is they're going to select a sample size. They're going to select 5, and in this case, 5 happens to be the same as the number that I marked. but it needn't be, but in this case it is. So they have their sample size. The number of successes in their sample is the random variable that we're after. We know about the population successes and failures and the sample size. That's these three things right here. So what we can do is we can go after this probability by using a hypergeometric distribution in R, basically by asking for the density of whatever point on this hypergeometric. So to give an idea of how you could do that, let's say in our scenario there, we could get 0, 1, 2, 3, 4, or 5 successes, correct? So what I want to do is I want to see the density of a hypergeometric over this vector given 5 population successes, 5 population failures, 5 in my sample. And what do I get? I get something like this. So we see that the what we can do is we can accumulate by using p-hyper on the same vector. Okay, so we look at this and we say to ourselves, well, look, the chances of my getting 1, 2, 3, or 4, sorry, my chance of getting 0, 1, 2, or 3 balls correct would be in this sort of 90% accumulated mass range. So that is to say that there's only about a 10% chance of randomly getting 4 or 5. Sorry, no, I've lied here, have I? Right, you've got a 9. Okay, so right, there's like a 9% chance, and then like a 9.5% chance, and then like a half chance of getting all 5. But basically, if your psychic is getting, I'd say consistently, if they're consistently getting 5, 4, or 3 balls, that means that they're consistently doing better than chance. If your psychic is able to get like 4 balls, like on command, they're really, really pretty amazing, in my opinion. Okay, so there's just an example of how you can approach this. Let's go to the next thing. It's Fisher 3. Good. Okay, so something bad happened, and I did like a page of work, and then I deleted it. But we're just gonna like plug through with this. So recapping what I've done, I identified when we can use this hypergeometric distribution in Fisher's exact test. No, I actually didn't. I never said it. So there are conditions that have to be met, and maybe I can just talk about them here for a second. You have to have a known number of trials, okay? You have to know at least one column total, let's call it 6, and at least one row total, let's call it 3. And here's the reason why. Once you know these things, the rest of the table sort of fills itself out. This one would have to be 4, this one would have to be 7. Now, in terms of the actual meat of the table, this is the beauty of this system, is that as soon as you choose any number in here, any number at all, the rest of the table is solved. There's only like one table configuration that has a 1 here. There's only one table configuration that has a 0 here. There's only one table configuration with a 2 here. And it's actually pretty amazing. I'm not really gonna show it now, but look. Okay. So I'll just show 2 sort of at once. So suppose this was like a 0 or a 1. And so this would have to be either a 3 or a 2, and this would have to be a 6 or a 5, and this would have to be a 1 or a 2. Okay. So if I hit a 0 here, I'm clearly talking about this table. And if I hit a 1, I'm clearly talking about this table. Now the interesting thing is that if you get a reveal on any one of these cells, it completely determines all of the other ones, meaning there's only one table that has a 2 here, and it's this table. There's only one table that has a 2 here. It's also the table that has a 2 here, a 5 here, and a 1 here. So basically, these tables are element-wise, they're like completely unique, which is pretty cool. Anyway, so this is our big condition. We've got to have at least one of these, and we've got to have this, and then we can sort of start imagining what our values could be. Okay, so I've shown how to move between a word problem, the hypergeometric setting, and a two-way table. Well, did I really show how to get into this two-way table? Yes, I did. I showed that, like, that should have been clear from the last slide. Let me just go back and take a quick look. So maybe I wouldn't have. So anyway, here's how you make it into the table. You know, you've got 10, that's the number of cards. We've been given that this is going to be me, this is going to be the psychic. This is what I did on that other slide that got deleted. And I'm either gonna check it or not. And you're gonna say I marked it or not. And we know that the total that I marked was 5. The total you're gonna say we're marked with 5, so that fills all the rest of this out. And then, as I said, pick anything here. 4. Okay, well, 1, 1, 4. Okay. So this this table just corresponds to what happens when you plug in 4 for your actual successes in your sample. Okay. Let's see another one. Where was I? That would be kind of sad if I didn't have any sort of conclusion about the answer. Now I want to show how to get the cute formula. Oh, so basically, once you've got your two-way table, there's like a really handy little thing that you can do, which is just you take all of those row and column totals factorial over all of your different cell counts, factorial times your big N factorial. So it's like it's a very easy shorthand for how to get at it. I guess like up here I just showed explicitly how you translate from a two-way table into the sort of more difficult, more computationally intensive hypergeometric PMF, which is like this thing, but it's understanding like where the terms in your hypergeometric PMF, like where they come from with respect to one of these sort of special two-way tables. Oh, so then I direct our attention to R to finish this problem. So I've assumed that the computer is going to show us how to do it. Well, I already showed this, but look. I know I've created some functions here that will do some hopefully useful things for us. Okay, so let's see a general Fisher on, well, I know that the number of success is this, this, and this, right? Uh-oh. That's a problem. Didn't like something I did. Okay, what are my arguments here? What have I done? Oh, so I like to do n. So for this function, so everything's based on each other, so it's like it's easy to go any number of ways. But I like to do a row total, which is 5 column total, and then the total n for the experiment. Okay, and I get something that should look a lot like what I saw up here, and it does. And then we can go look at our picture. And so this sort of corroborates what I was saying before. The most likely things are to get 2 or 3 right in this situation. You know, once you're starting to get 4 or 5 right, you're starting to do something that I would consider very impressive. If you're consistently performing at like 2 or below, I would say that not only are you not a very good psychic, but you should probably do the opposite of whatever your psychic intuitions are. Okay, that gives us some good closure on this problem. Let's move on. Okay, next scenario where we can use Fisher's exact test to figure out how your goalie is performing. Now, before we start taking this to the sports betting venues, to the off-track betting or whatever, I guess you don't do off-track betting on soccer, but this problem is about soccer and it's not about soccer. There are some similarities, but it's a highly contrived game. So you probably already noticed this, but each example I'm giving has like something. Actually, the psychic one is pretty good, because in that case, the thing that doesn't have to do with reality is the person's claim in their ability. But like, basically my point is, in each example, there's some fictional element that we have to accept. And this will certainly be no exception. Okay. So in our little world, the soccer game consists of shooting 10 shots on goal. Now the kicker only has 2 strategies that they choose from. They either kick left or they kick right. The goalie has 2 strategies, which is to block to the left and to block to the right. Further, knowing that there's going to be 10 shots, both the goalie and the kicker have devised strategies for how many times they're going to allow themselves, or how many times they're planning to go in certain directions. So the goalie has said he's going to jump to the left 3 times out of the 10, but you know, it remains to be seen when he's going to choose to do that. Hopefully it will be skillfully and at appropriate times. And the kicker has also decided in advance that they're going to kick to the left only 2 times. The rest of the time they're going to kick right. So you calculate your probabilities using what we tried to learn in the last slide. And you watch a game. So what kind of numbers of goals scored would cause your eyebrow to raise? Like, are there any outcomes here that would be suspicious in any way? like, what would you have to see in order to sort of come to the following conclusions, that either there's something funny going on and your goalie is in a conspiracy with the kicker, or your goalie is just like not very good but is probably not, conspiring against your team. Maybe your goalie is performing acceptably, or maybe your goalie is doing a really amazing job. So how would you actually compute this? So what I did is I made my little table. My goalie can go left or right. Okay. My kicker can kick left or right. I know that the total number of kicks to the left is going to be 2. And I know that the total number of goalie jumps to the left is going to be 3. And I know that there's 10 total games. So the rest of this guy fills himself out. I just gave this one example where, there was one correctly identified left kick. Now, an interesting thing about this table is that left is an outcome that we've sort of emphasized, but at the same time, if they both go right, then the goalie gets a save also. So we're then looking at the probability. We need to equate the probability of one left with the overall probability of there being 7 stops out of 10. I'm going to show that on the next page. Okay, this is just what I was saying. We have a probability distribution, but we aren't quite done because right is also a successful block. We have to extend our result. And so by that I mean we get our probabilities of the different numbers of lefts that could possibly occur. This number is limited by the total number of lefts in the population, meaning the total number of left kicks that the kicker is going to do. 0, 1, 2, 3, and then we look sort of at the diagonal of these tables to get what's happening in the other slots. So if there were 0 left coincidences, that implies that there were necessarily 5 right blocks. 1, as we said, is going to map to 7, and 2 is going to map to 9. So, what do we see here? What have I said? In conclusion, I'm confident in saying that if the goalie is at 5 saves consistently, then he's either sucking or conspiring. And I say that because to get only 5 saves, he would have to miss all of his left guesses. And the probability of that happening is under half. So if this keeps happening more than half the time, then you would think that something funny is going on with your goalie. Okay, if you had sort of a healthy mix of 5, 7, and 9 saves, then you would probably say that there was nothing too crazy going on, because you would expect sort of half the time he should be getting a 1 or a 2, which would be a 7 or a 9. So if you're getting like some 7s and 9s in there, with your 5s, then like that would be like acceptable. Now, if he's consistently getting 9 saves, that would be very, very impressive, and you would want to hold on to that goalie because it would mean that he's doing much better than chance at stopping the balls. By chance alone, you would only expect to see this kind of result 6% of the time. So something that's only likely to happen 6% of the time is happening consistently. You can assume that your goalie is pretty good. Okay, we're getting close, guys. Let's be patient. Okay, then I go through and I do an odds ratio. I did something funny here where I had to make this cell a half. I went through and I computed it, and it was something huge. So you might say that like in this scenario, well, what could you say? you could certainly say that, like, given that the kicker has gone to the right, there's like a very, very good odds that you've also chosen to go to the right. I'll leave it at that. I'm not happy with any of that, but someone can help me out with that if they are a phenom. Okay, and now my favorite one. So is the girl you like avoiding you? Quite possibly. No, she'll be home soon. I hope. I mean, look at how late it is. Okay, suppose you know that she goes to the library 5 times a week. At whatever time, but it's always the same time. She always goes at noon. But you don't know what days she goes to the library, and you've been sort of trying to study her behavior, and you can't find any sort of pattern. Now, your objective is you want to, like, run into her as much as possible at the library. But you don't want to feel desperate, so you've limited the number of times you are allowed to go to the library to 4 times a week, which you also, you don't really know. You don't know her pattern, so you just sort of like pick 4 days randomly also and go to the library. So you head to the library to hopefully have a chance encounter. So what are the probabilities for the different possible number of encounters you could have in a given week? Okay, well, this is a super straightforward application of everything that we've just done. Okay? We know that she will either go to the library or not, and you on a given day, and you will either go to the library or not on a given day. Total number of days is 7. The total number of days she goes to the library is 5. Total number of days you go to the library is 4. So then based on your number of successes, the rest of the table fills itself out and implies a probability. So let's just, for argument's sake, let's go with we'll go with 4, 0, 1, 2. So, you know, it actually just came to my attention that I never actually showed how to move from this to the hypergeometric. Maybe just to prove that I can do it on the fly or that I'm actually comfortable with it, we can do it here. So to get your hypergeometric probability, the way you would build it is, okay, you've got to take population successes, which is 5, choose sample successes, which is 4, times population failures, which is 2, choose sample failures, which is 1, oops, sorry, this is population successes, choose sample success, times population failure, choose the remainder, oops, I switched, no I didn't switch these up. This is what she does, this is what you do. The number of times you don't go to the library. So population sample success, population success, choose sample success. times population failure choose sample failure divided by total population choose choose sample. So it's got to be that. Let me see if I can confirm that with the hypergeometric. Dhyper for, okay, in the population, there's 5 successes, 2 not successes, and my sample is only 4. Right. So there's a 14% chance of this guy. Now let's see what happened if I had done my general Fisher of rowtot, column-tot. Is that the way I did it? No, I would have said column total. So her successes were 5. My total goes to the library were 4. And the total number of days was 7. Okay, and so this should model it pretty nicely. And does this allow us to make any conclusions? Well, what have I said on my beautiful thing here? So we take a look, and we can say something like 86% of the mass is ahead of the 4th rendezvous. So, meaning, if you're seeing her, if you're seeing her 0, oh, you can't see her 0 or once. You're gonna see her. If you see her once, if you see her twice or 3 times, that accounts for 86% of the mass. Now, when you start seeing her that 4th time, you're starting to look at a rare event. So, if you only ever see her twice, meaning you're like stuck in this probability, then she is avoiding you, or there's some systematic scheduling consideration that you don't know about. But basically, there is a relationship between the 2 variables. They're not behaving, they're not freely behaving randomly. Now, if you consistently see her 4 times, then you should proceed and do something about that because because seeing her 4 times would be rare indeed. So if this was happening often, that would be somewhat suspicious. Okay, and I did go through and do an odds ratio for this one in the case of like 3 rendezvous, and it was something sort of unspectacular. You know, in terms of with this kind of odds ratio, you could say that the odds are 1.5 to 1 that times that I went to the library, she was there. That the odds are better that she was at the library when I went than they were that she was at the library when I wasn't. Right, which makes sense, because if you went 3 times and she was there each of those times, and you didn't go twice, there are 2 times where you didn't go that she did go, and here there were 3 times that you did go that she also did go. So, you know, I'm obviously not that good yet at doing the odds ratio stuff, but I think I've made some leaps and bounds with my Fisher's exact test, and I hope that everybody enjoyed the simulation. And what I will do is I will copy and paste this function into the YouTube video so that everyone can take a look. Okay, thank you.